Modern fleet telematics has successfully solved the problem of asset visibility. We now know with absolute precision exactly where every vehicle is at all times. But that perfect visibility creates a secondary crisis. Sensors now generate up to 25,000 data signals every single minute. This flood comes from deep tap sources running simultaneously across the vehicle: GPS tracking, CAN bus metrics, fuel level probes, and electronic cargo locks. Conventional software platforms fail because they route all of this incoming telemetry as urgent, red alert dots directly to dispatchers, who are already on the phone, managing routes, and putting out fires. Solving this bottleneck requires framing the volume of data as a delegation problem. The solution is a unified architectural data spine built to support three distinct postures of AI workflow: Ask, Human in the Loop, and Autopilot. Turning pure data noise into trusted action requires a system designed to decide exactly who acts on a specific signal and precisely when they do it. Before assigning any workflow to an AI model, the system must establish a rigid data foundation. The plumbing has to be fixed by normalizing incoming signals and structuring the entity graph. Signal normalization ensures the math is consistent. A harsh break must trigger the exact same metric threshold across a Volvo, a Ford, and a Tata. This relational diagram illustrates the entity graph. It prevents data silos by creating a permanent, queryable web linking a specific truck to its current driver, the assigned geographic route, the physical telematics hardware, and the underlying business contract. With the graph structured, the processing architecture built on AWS must physically map data computation to data frequency. High-frequency telemetry, like EMA CAN data at 100 Hz, is filtered at the edge using AWS IoT Greengrass to preserve cellular bandwidth. Above, ingested signals stream into Kinesis and TimeStream, powering SageMaker and Bedrock for cloud intelligence. This end-to-end data spine provides the technical context needed for models to generalize across manufacturers and for automated actions to remain verifiable. The first AI posture is Mode 3, Ask. This is engineered specifically for operations directors who need immediate answers but will never manually hunt through a telematics dashboard. It functions as a plain language layer that queries across all feeds to instantly resolve complex logistical questions. An operations leader can type a single prompt asking which regional depots are experiencing worsening fuel efficiency and whether the root cause points to driver behavior or declining vehicle condition. To build trust, this mode requires strict rules. The agent must explicitly cite the specific systems it queried and define the exact time window it analyzed to reach its conclusion. The agent must also actively identify its own blind spots, clearly stating if specific vehicle sensors were offline during the queried timeframe. Silently averaging over missing data destroys operational trust. An honest AI that explicitly cites its work bridges the gap between raw backend databases and human decision-makers. Mode 2 is Human in the Loop. Across modern fleet operations, this specific mode drives the highest measurable financial return on investment. Historically, fleet software failed here by forcing human operators to manually review and approve every single alert. That exhaustion trains workers to click yes without reading the details. This split-screen comparison shows proper execution. The AI handles 95% of the heavy investigative work on the back end. It then presents the operator with a finalized, logical decision to review, rather than a task to complete. This review is mandated for high-stakes events, like modeling overhaul downtime costs or drafting driver coaching packets based on harsh braking data. Anything that formally accuses a driver of cargo theft or removes a physical asset from revenue-generating service must remain human in the loop to prevent expensive, irreversible errors. On the back end, AWS step functions suspend the workflow logic, issuing a secure task token until a human provides an explicit approval or rejection. Every time a human rejects an AI proposal, the system logs the exact reason. That rejection becomes direct training data to refine the model's accuracy. Human in the loop prevents operational catastrophes today while safely conditioning the underlying models for autonomy tomorrow. Mode 1 is Autopilot. Here, the agent runs continuously in the background, processes incoming data, and takes immediate action without asking. The threshold for this mode is rigid. Autopilot is reserved strictly for high-frequency, low-ambiguity decisions where the financial cost of a false positive is incredibly cheap. A highly effective example is auto-closing dashcam alerts triggered by false positive lane departures. The AI clears the noise automatically, saving safety managers hours of tedious video review. The engineering mechanism that makes unattended action safe is multi-feed correlation. A 40-liter drop in a commercial fuel tank viewed in isolation is just noise, lacking context for automated action. But as additional telemetry locks in alongside it, stationary GPS, engine off, opened cargo lock, and zero card transactions, it instantly becomes an undeniable fraud case. The absolute requirement for autopilot is accountability. Every automated decision must generate an immutable, replayable audit log, recording its inputs, timestamps, and mathematical reasoning. The capability to correlate multiple live feeds and permanently log the reasoning is what separates a truly autonomous agent from a basic rules engine wearing an AI badge. Ask, human in the loop, and autopilot represent a single data workflow moving through 3 specific stages of maturity. When an operations director manually asks the same question enough times, the engineers wrap it into a prepared action for a human to approve in the loop. This trust ladder pipeline visualizes the graduation metric. Once a workflow hits a boringly high human approval rate, the system automatically promotes it to autopilot. This promotion is gated by 4 strict rules. First, the cost of being wrong must be negligible. Auto-closing a false dashcam alert costs nothing. Grounding a vehicle costs thousands. Second, the automated decision must be easily reversible. If an action cannot be easily undone, it stays in human hands indefinitely. Third, the action cannot touch a person's record. Anything affecting a driver's employment, paycheck, or safety score is strictly gated from total automation. And fourth, the decision must be mathematically replayable. If you cannot perfectly reconstruct the sensor readings 6 months later for an insurance dispute, the workflow cannot be automated. Long-term efficiency belongs to the fleets that engineer systems to safely offload low-value decisions.